All right, let's jump right into this explainer and channel our inner medical detectives. Welcome, everyone. Today, we're going to uncover the hidden flaws and mathematical illusions that actually lurk within the medical literature. I mean, we rely on data to make literal life and death decisions, but what exactly happens when the data itself is wearing a mask?
It's a pretty provocative question. We really have to ask if the ultimate evidence we rely on to treat our patients is infallible or if it's, well, systematically distorted. We're taught from day one to revere the gold standard. But as you're going to see, even the absolute strongest evidence is vulnerable to manipulation. And that leaves our most critical clinical guidelines hanging right in the balance.
Here is our roadmap for today. 1. The evidence gold standard. 2. The threat of bias. 3. The file drawer problem. 4. Distorting time and survival. And finally, 5. Defending the data.
Okay, let's kick things off with Section 1, the evidence gold standard. Think of systematic reviews and meta-analyses as the absolute heavyweight champions of the evidence world, sitting right at the peak of the hierarchy, above randomized controlled trials. By mathematically pooling massive sums of data from multiple studies together, they give us incredibly precise answers about drug efficacy. It's basically like combining all the best data into one giant super study. Now, when researchers mathematically pool this data, they have to choose a mathematical model. They'll use either a fixed effect model, which just assumes there's one single shared truth across all the studies, or a random effects model. And the random effects model is pretty clever because it accounts for the messy reality that clinical effects often vary across different trials due to things like different patient populations or slightly different protocols. But what happens when the foundation of all that is cracked? That brings us to Section 2. The threat of bias. So, meet our main antagonist for the day, bias. And look, bias isn't just a random mistake or a little statistical blip. It's a systematic error that pulls our clinical conclusions dangerously away from the true, real-world value. Random errors, they just add noise. But bias actually points us in the completely wrong direction. Which leads us right into how that bias hides in plain sight. Section 3. The file drawer problem. Let's talk about publication bias. It happens because, let's be honest, sponsors and journals absolutely love a shiny, positive breakthrough. So what happens to the trials with completely null or negative results? They get abandoned in literal file drawers. But there's another insidious layer here, called time lag bias. See, highly significant, positive trials get rushed into high-impact journals within months. But when negative trials do get published, they face prolonged delays, rejections, and endless revisions, getting trapped in the publication pipeline for years. This real-world medical board scenario is a direct warning about this exact trap. If a systematic review or meta-analysis solely aggregates the currently published literature, it creates a massive mathematical distortion. It ends up capturing all those early, highly polished positive trials, but it completely misses the negative data that's still stuck in peer review or abandoned in a drawer. The result? It heavily overestimates a drug's true efficacy. So how do we actually catch this invisible distortion? Well, you grab your detective's magnifying glass, which in our case is the funnel plot. This is a brilliant visual tool that maps out every single study's treatment effect against its sample size or precision. If you've got a beautifully balanced literature base, you'll see a symmetric, inverted funnel. Large studies at the top and an equal spread of positive and negative small studies down at the bottom. But if you look at an asymmetric funnel and there's a glaring gap in the bottom corner, yeah, that confirms that small, non-significant trials have been systematically hidden from us. We're literally missing a crucial piece of the truth. Publication bias isn't the only illusion out there. Let's move to Section 4, distorting time and survival. It is absolutely crucial to contrast these two really tricky biases. Lead time bias happens when catching a disease earlier falsely makes survival appear prolonged. You didn't actually extend their life, you just started the stopwatch sooner, but the actual death date remains exactly the same. Length time bias is different. That happens when a screening test preferentially catches slower, indolent diseases. It inflates the test's apparent success, because essentially you're catching the slow-moving turtles and completely missing the fast-moving rabbits. Shifting gears from time over to human behavior, we also have to differentiate between recall bias and the Hawthorne effect. Recall bias is when patients who are already sick obsessively overreport past exposures. right? They're racking their brains for a reason why they got sick. The Hawthorne effect is totally different. That's when participants alter their behavior and act healthier simply because they know researchers are watching them.
The bottom line here is you just cannot trust human memory. To fight off recall bias in case control studies, the absolute best defense is anchoring your data with objective measures. Validating a patient's self-reported history with something indisputable, like an objective blood test, completely neutralizes that bias.
All right, final stretch. How do we protect our guidelines? Section 5, defending the data. We protect our patients by rigorously vetting the data. First, identify the outcome and the effect size. Second, ruthlessly check if the confidence interval crosses the null value. But systemically, we need bigger defenses. To combat publication bias, modern trial registries now mandate that studies are registered before a single patient is ever enrolled, allowing us to hunt down that unpublished data. And for time lag bias, we can run a cumulative meta-analysis, adding studies chronologically by year. If a treatment looks amazing early on, but the effect systematically trends downward as time passes, and those older, delayed trials finally emerge, boom, you've caught time lag bias in action and stopped premature hype in its tracks.
I want to leave you with one final, really provocative thought to chew on today. Just because a massive meta-analysis proves a mathematical difference, does it actually matter for the patient sitting right in front of you? A huge sample size can literally make a meaningless difference look statistically significant. So always remember, statistical significance does not always equal clinical significance. So keep your medical detective hat on, keep questioning the gold standard, and keep digging for the truth.